right, so we're going to go through some disk method examples, and I'm going to take you through a PowerPoint presentation that I've used in the past so you can see the setup of the problem. I'm even going to give you a visual idea of how the problem works, kind of everything that you need to know in order to do this. So first one has the function f equals x cubed minus x plus 1. X equals -1 and x equals +1 are the boundaries. We are going to revolve it around the x-axis. And then kind of my general note here, when I think it's important to draw like what I call a sample radius, your sample radius will always run perpendicular to what you are revolving around. So here's my function. This is the x cubed minus x plus 1. And I'm revolving it around the x-axis. So here's kind of my general picture. Now keep in mind that this top region is really the only original region that's created, and then when I revolve it, I get this kind of image underneath that is kind of a reflection of it. And that's a general idea of what my three-dimensional image looks like. In my mind, it kind of looks like a doorknob. So what you're going through and doing here is really just establishing what is the radius. So when I'm doing this, my radius, and this is what I think is important to draw, is just one sample radius of what one of my disks would look like. Now, my radius is going to be represented by, in this case, the function, because depending on how high the function goes or how low the function goes, you will always get that length right there as my radius. My boundaries, the other thing that I need to know, are -1 and 1. So this one's given to you. Sometimes the boundaries are a little more complicated to find. So my setup should look like this. My radius is x cubed minus x plus 1. My integral goes from -1 to 1. You're always going to have a pi out front. That is constant, comes from the volume formula. You're going to plug it into your formula for volume, which is going to be having the radius squared. Obviously, your calculator is going to be huge for this because you're not going to be doing this by hand. I leave the pi out front and then just attack my pi on the answer. So when I do this on my calculator, I'll go to Math 9 and I'll type in my boundaries and I'll put the function in parentheses and put the squared out there, but I won't put the pi in. Now, when you are doing problems like on Delta Math, they will have you multiply the pi through and ask you to round your decimal. I like keeping it nice and clean and keeping the fraction form times pi. It truly just depends on what platform you're using. So that's our first one. This is just kind of an overall summary of what we're doing here. So the idea is if we're revolving around a horizontal axis, so horizontal axis being something like this, like your x-axis is the best example. When you write your formula for volume, your boundaries are going to be A and B, so where we start and where we stop, those are x values, and then your radius is going to be in terms of x's. So if you're going around a horizontal axis, and so you're revolving around something like this, everything's going to be in terms of x's. Your boundaries are going to be x's, your radius is going to be x's. If you're going around a vertical axis, so let's say you're taking a function like this, and you're revolving it around the y-axis, so we'll kind of start and stop here. What's going to happen now is your boundaries are going to be in y. So you're thinking of taking like that tuna can and slicing it from bottom to top. So these c and these d values are y values. Think of it as putting one disc on top of the next on top of the next, like you're stacking, almost like the child's toy you play with where you put the rings on top of a stacker. I don't know if any of you know what I'm talking about with that. And then your radius is going to originate from your axis, and it's going to run perpendicular to that, and your radius isn't going to be in terms of y's. So if I'm going around a horizontal axis, everything's in x's. If I'm going around a vertical axis of revolution, like the y-axis, it could be other vertical lines, everything is in terms of y's, your boundaries and your equation that you use for radius. Let's get back to the examples. So here is one that is a function, the square root of sine. I drew a picture of it. It looks kind of like just an arch, like a rainbow. And we're going to revolve it around the x-axis. And we're going from 0 to pi, which is actually what's on my picture. So revolving it around, I get something that looks like that. It's very much in my mind like a football or a blimp that's going on here. So when I think of my sample radius, I'm going to draw a picture here. My sample radius is like this. It again is just going to be represented by the function of x. We are going to be in terms of x. My boundaries are given, they're 0 to pi. So here's my setup. My radius is just the function square root of sine. My setup is going to have pi out front, and then the integrating from 0 to pi of the square root of sine of x being squared, which is just going to end up being integrating sine. When you put that in your calculator, or you could actually do this one by hand pretty easily, you get a volume of 2 pi. We usually don't put units on our answer, but realize it is volume, so it is cubic units. So here's one that we're going to revolve around the y-axis. So you'll notice right away that even my function is in terms of y. So it's x equals y squared. We're going from x equals 0, y equals 4. That's going to enclose my region, and I'm going around the y-axis. So here's what it looks like. This is what the equation y equals x squared looks like. X equals 0 is just the y-axis. Y equals 4 is going to be a horizontal line. So this is my original region, and we're revolving it around the y-axis. So now when I think about my sample radius, I'll draw it in a different color here. My sample radius is going to go this way. It's going to run side to side. It's going to be perpendicular to what I'm revolving around. So for my setup, here's my picture. It looks kind of like a funnel, but it is completely solid. There is not a hole in the middle. My radius is going to be, again, the equation y squared. There will be times my radius will be something different, I promise, but I want to start with the simple ones. I am integrating from 0 to 4. So this is from my low height to my high height. So that's what my boundaries are. It's like you're stacking those cylinders on top of each other. So you're going from 0 to 4 of your radius squared, which is y squared squared. Put the pi out front, you get 1024 pi over 5. Using the same region, so this is the exact same picture, and they do this a lot on the AP test, but they're going to change what we're going to revolve around. So now instead of revolving around the y-axis, now we're going to revolve around the horizontal line, y equals 4. So when I go around a horizontal line, I want to go back to x's. So now my radius is going to originate at my axis of revolution. It's going to be that length right here. That's going to be my radius of my discs or of my cylinders. So now, this is just all the given information. So now my radius is going to be this length, which is the length is going to be 4, which is going to go from here. Let me do it in a couple colors because I think it makes more sense. 4 is the length from here to here. But I don't want that entire length. I want to get rid of everything that is beneath the function. So let me put that in black. This is my function square root of x. So to get this radius, I'm going to take my 4, which is my red, and I'm going to subtract off what is under the function. I think of it as finding a radius as doing the top minus the bottom is a great way to think of it. So my radius is going to be 4 minus my equation, y minus my function square root of x. And it does need to be in terms of x's. So again, you'll notice that when I put it into my equation, into my formula, I have a pi out front. My boundaries are x's. So it starts at 0, which is obvious, but then it stops here. And this is when x is 16. And the way I know it's when x is 16 is it's when y is 4. So if I put 4 into here, 4 squared is 16. That tells me the x value that goes with y equals 4. So I am slicing it into discs like this from 0 all the way until we get to 16. So that's my boundaries. My radius is top minus bottom, so 4 minus the square root of x. I have to square all that. Now I want to tell you something about your calculator. When you put a function into your calculator to integrate and it has a radical in it, for some reason the calculator goes a little berserk and it will not put your answer in a fraction form. It actually ends up being exactly 42 and 2/3, but for some reason the calculator hates that square root and it will keep writing it like this. The good thing is we can still write it out to 3 decimal places. Here's my picture. That's what that would look like, kind of approximately. The pictures are kind of fun to see. So here's one where my function is 2 minus x squared, which is just going to be like an upside down parabola. And the horizontal line, y equals 1. And we're going to revolve it around that horizontal line, y equals 1. So here's what my region looks like. And we're going to revolve it around this line. So my boundaries, I'm going to have to find my boundaries algebraically, or I could do it on my calculator. If I set 1 equal to 2 minus x squared, my boundaries are going to be -1 to +1. I could also go from 0 to 1 and double it. I could kind of use the symmetry, or since I'm using a calculator, I could just go from -1 to 1. So my radius, When I draw my radius, that's going to be an example of my radius. And again, I want to find this length by taking the top curve, which is the parabola, minus the bottom curve, which is the horizontal line. So my radius, oh, there's a picture of that. My radius is going to be 2 minus x squared minus 1. So you're taking 1, you're basically taking this distance off of that radius. You're getting rid of that 1 space. So you have 2 minus x squared minus 1, or another way to write it is 1 minus x squared. Your boundaries are going from -1 to +1. You're going to take that radius and square it, and then you're going to put it in your calculator and make the calculator do all the heavy lifting to get 16 pi over 15. If you're doing delta math, you can multiply the pi through and get the decimal that goes with it. So here is one, the square root of x. Square root of x, you should know what it looks like. Y equals 0, x equals 4, and we're going to go around the x-axis. So here's my picture. This is the square root of x is this blue function. Y equals 0 is just the x-axis. X equals 4 is this horizontal line. So that's what x equals 4 is. And we're going to revolve it around the x-axis. So this is our kind of 3D image that we get. When I draw my radius, this is going to be my radius. And when I write that radius, it's just going to be my function. My boundaries, I'm going to start my slicing here at 0. I'm going to end my slicing here at 4. So with my setup, there's my radius. There's my integral. Again, I am squaring the square root of x, so I end up with just x. I can integrate it with a calculator, or this one would also be very easy to integrate by hand. And then I get 8 pi, or the decimal equivalent if you want to multiply pi through. Now, if you take this exact same region, the same little gray region right here, we can actually do other things with it. We can take that same region and we can revolve it around the vertical line, x equals 4. When I revolve around a vertical line, everything has to be in terms of y's. So now when I'm slicing here and I'm going up like this. So if you think about my region, I'm slicing it like this. My radius will be this length. Let me put it in different colors so it stands out a little bit better. This is going to be my radius. And my slicing is going to happen from this height 0 to this height 2. So when I write my radius, when you're doing a radius and it's in terms of y's, what you want to think of is think of right minus left to find that radius. So the right curve is this vertical line, 4, and the left curve is this square root of x, but we want to write it as y squared. So it's going to look like this. There's my picture. I think it looks like the top of an acorn. So 4 minus y squared is going to be my radius. That is right minus left. That's where that comes from. And then my boundaries are going to be 0 to 2. So I have my radius squared, 4 minus y squared, all being squared. Really nice to have a calculator with this. I'm going to plug it in my calculator again, Math 9, and I'm going to get my answer. I'm going to keep it as a fraction. You could also write as a decimal if you want to multiply pi through. You get 256 pi over 15, and that is the volume of this kind of acorn cap that we're looking at. Here's one from our book. This one, you have lots of different curves. You actually create a trapezoid. So you have y equals x, which is going to be this one that runs like this. You have x equals 0, which is going to be this one. Sometimes it helps to use color coding here. You have y equals 4, which is, let me put that one in black. That is this horizontal line. And you have x equals 6, which is this vertical line. So we get this enclosed trapezoid. And we're going to revolve it around the vertical line, y equals 6. So when I do that, I get, this always reminds me of on the circus what the elephants stand on, kind of like a truncated cone is what it looks like. So my radius, since I'm going around a vertical axis, my radius is going to be in terms of y. This is going to be an example of a sample radius. My boundaries are going to be y, so how low and how high do I slice? So I start slicing here, I stop slicing here. When I write my radius, I'm going to do right minus left to find that length. So here's kind of everything I just said in setup. So my radius is going to be 6, that's the vertical line, minus your function y, or y and x are interchangeable in this. My boundaries are going to go from 0 to 4, because that's the low end to the high end. And my radius is being squared, and I get a 208 pi over 3. So that is, again, my volume that is enclosed of this funky looking truncated cone. That is going through all your basic examples. What we're going to do next is we're going to talk in class about what happens if this region isn't solid. What happens if there's a hole in it? How do we deal with that? But for now, we're going to focus just on the ones that end up being pretty perfect, especially with a calculator to find that volume. Get out of this and get out of this.